This is an introductory video showing you a quick RAPT run. It's not going to go into huge detail in each of the sections. Those will be dealt with in separate videos, but it will just do a quick run to show you roughly how a slab run or beam run is created and what the outputs look like and how to navigate. Let's create something new here. Click on the new button. We click new and OK for frame. We're not going to go into the details here because this is a wizard to create something new. I'm just going to click OK, and we can come back to this in another video on what all of these mean. Let's click OK just to get into the detail. On the left hand side here we've got our inputs, and it's generally broken up into options that apply to the entire run. Your frame input, which includes spans, columns, any changes to the slab, including set downs, penetrations, what have you. We have our loads, and then we have reinforcement on the bottom left, and that is where you put in design zones for RAPT to design reinforcement or your own user-defined reinforcement. RAPT will add reinforcement where you haven't provided enough. And then we have design data here, which are further options that are specific to areas including ultimate limit state, crack control, deflection, etc. We have a materials tab, which include materials that are specific to your country and your code. So at the input page here under general, you've got your design code, and then you've got your material. And that material, which you've selected there, determines what is in the materials page here. You can change these settings. So if I look at the concrete setting, you can see there are different concrete strengths. You can change those concrete strengths and change the creep characteristics, the tensile strengths, all of those things. Typically you wouldn't need to change anything there, but you can. And similarly with reinforcement bar, you can add your own custom reinforcement bars. It's quite helpful if you're doing any historic work. Back to the concrete, I want to mention that RAPT uses a stress strain curve to do all its design. That includes column design, any flexural design. So instead of using a stress block, which is the simplified method, RAPT will integrate the stress strain curve to determine the concrete compressive force. Going back to input, we will get to output. That's after you've put everything in for a frame, and we'll show you what comes out at the end. So let's kick off. We're selecting a code. I'm going to stay with AS3600 for now. We're just going to do a reinforced section, and you can either do a slab or a slab with a beam. So it's going to be a slab with a beam. It's going to be one way, and that's pretty much all we need to do on this page here. So let's go to our spans. We click on spans here. We have a left end. I'm going to put in 200 millimeters here. Actually, I might make this 300. Our span's going to be 8 meters. If you want to repeat data in cells, you hit Control R. So let's make the slab thickness 200. I hit 200, and then I hit Control R, and that populates the rest of the field. Let's make the span width 5 meters. Control R, populates the rest of it. Okay, our right end is 300. Now the important bit here is the right end and the left end, because RAPT will always need some, and in fact all structures do, need some extension beyond the support point so that you can develop bars and get tension into the bar before your bending moment starts, because obviously you have an offset in your bending moment diagram that needs to be accounted for with the truss effect. Okay, spans are now done. Now we can look at our columns, but before we do that, let me just show you how RAPT works in terms of moving around the section. So you can see that RAPT takes sections looking to the left, and RAPT will always give you a distance to grid. So at the moment, to grid 1 is 5635 millimeters. 5635 millimeters, and to grid 2 is 2364 millimeters. The other thing you can do is you can change the scale. So you can look at in scale and then not to scale, which is just makes it easier to look at your reinforcement. You can look at a full elevation, which doesn't make any difference here because we haven't got any columns. But when you have columns, it'll show the full height of the columns. And you can look in plan. So at the moment, it doesn't show much. You just got a center line and a slab. But it'll start to make sense when we add columns. So let's do that. Go to columns, and we're going to change this from a knife edge to a column. And again, I'll repeat that all the way down. Control R. Let's make them 3.5 meters up and 3.5 meters down. And you can see as we put that in, then RAPT gives you the opportunity to add in column dimensions. If we want a circular column, you put in a dimension here. Let's call it 600. And then the dimensions for the rectangular column are no longer available. Here, let's put in square columns, 400 by 400. And then the circular column dimension disappears. Now, if you want to change that, you just delete these and then you can add in your circular column if you want. Okay, so here are transverse column spacings. The important bit here is that RAPT works on a equivalent column, uses the equivalent column method. If you're not aware of what that means, you should read that up in any textbook. It's widely used, and it's essentially a way of calculating the torsion that's generated in the slab to get into the columns. So, for example, here on our slab, which is in plan, you can see now that we've got our plan view. It's added columns. At the face of the column, bending moments will be taken into the column. But there will be also a portion of bending moment in the slab that's taken into the side of the column. And the equivalent column method is a way to calculate that total moment that goes into the columns. Next up is just that elevation, which I said I'd show you, which that's now to scale. That's to scale. That's not to scale, but you see the full elevation, and then that's a sort of a close-up of the slab so that you can see your reinforcement. Now let's add a dimension in for the beams. So I'm going to make these beams 450 deep. I'm going to make them 600 wide at top and bottom. You can make them taper if you want. So if I added 400 here, you would see a taper. Let's just keep them 600 top and bottom. I'm not going to add any drop panels nor any transverse beams. If we take a section here, you can see the beam. And layers, elements, and steps, they are ways to achieve full steps in the slab. Vertical upstands on the left or the right, the center, you name it, you can do it. But it's a little bit more than we have time to show in this tutorial, so we'll skip that for now. There will be a specific one on that later. One thing I should show you is back on your beams, RAPT calculates your effective width in the flange based on the points of contraflexure. Then we go into cases. We're going to add loads into this now. So we've already got a self-weight load case, and that's applied as a line load. You can't change that unless you request to change that under general, and you can change that under self-weight definition. But let's go back to cases. We'll add in two other cases. Let's add in initial dead load. Let's add in live load, and then let's add in extra dead load. Extra dead load being the dead load that's applied after brittle finishes or once brittle finishes are installed. So RAPT calculates a number of deflection quantities. You have your short-term deflection and your long-term deflection. You also have an incremental deflection, which is not quite your long-term minus your short-term, and you can get more information on that in the help or in the videos that we'll provide on that. But that incremental deflection is essentially the deflection that partitions, brittle partitions or brittle floor finishes will see over their lifetime from when they're installed to end of life. Okay, let's add the load. So we've got initial dead load. I want to add a load, full panel width along the full length of the frame. So it's going to be 2 kPa. I'll do the same thing with live load. I'll add 3 kPa. Extra dead load, I will add half a kPa. Let's say they're tiles. Okay, now we've got our live loads, all our loads put in, and now we can look at our combinations, and the combination cases here are shown. They're derived from the code. You can change the factors if you want, but they will be in line with whatever code you've selected under General in the top left. Then we've got short-term service. These are combinations that are used to determine your crack control. Permanent and characteristic service combinations are Eurocode specific. We have deflection load cases. As I was saying before, we have a short-term deflection, we have a permanent deflection after 30 years, and we have an initial deflection, which occurs when the slab is first poured. Not when it's first poured, but after 28 days. So the short-term and the initial don't have any long-term characteristics, no creep or shrinkage. And then using those 3 combinations, RAPT works out what the incremental deflection is. We have transfer prestressed, which is for post-tensioned or pre-tensioned systems. And we have pre-existing load cases, which is where you might add reinforcement to a structure that has already been built. So carbon fiber strengthening, for example. Let's go to our reinforcement. So these are the defaults that RAPT will use when it puts in reinforcement. We'll go to that again, that'll be dealt with in another video in more detail. Design zones. We have some design zones set up already. Let's go to our user-defined. So I'm going to add some user-defined reinforcement to the bottom of the beam. I just go to bottom and I add bottom bar. Click OK, and I will add 5 N16s. Okay, so now we have a user-defined reinforcement here. Anything that is not adequate, if there's not enough, RAPT will add reinforcement. Design data, these are options for various parts of the design. We won't go into those in detail now, we won't need to change them. So let's go to output. Let's start with our bending moments. So RAPT shows you results for the individual load cases and for the load combinations and the envelope cases. So here is the flexural bending moment, combined bending moment, or envelope case I mean. And you can click on these labels here, and then if I select along the beam, it'll tell you what the values are along any points along the bending moment. RAPT will already give you the worst case hogging and sagging bending moments, and similarly for shear, it'll give you the shear at the face of the column. Okay, the bending moments are one thing, but obviously you need to design to those bending moments. So you go to here to flexural design, and RAPT will give you 2 outputs. One is text and one is graphics. They show similar things. Let's start with ultimate design. So at each location along the span, RAPT will tell you what the design bending moment is, what the minimum moment is, the minimum being 1.2 times the cracking moment. It'll give you an initial condition. So in other words, this is based on the user-defined reinforcement we put in. And you may remember we put in reinforcement at the bottom of the section. So there's no hogging capacity, but there is sagging capacity. Here is the final condition after RAPT has added reinforcement. And you can see that now, for example, the bending moment capacity is 255 kilonewton meters against a design moment of 244 kilonewton meters. And it has added 1,542 millimeters squared of reinforcement to achieve that. RAPT also shows you reinforcement required for shear and for crack control. And if I go to this ultimate graph, this graph shows you the reinforcement that was added for flexure. So top ultimate, for example, shows you the reinforcement that was added to achieve the flexural capacity for hogging. Top total is the reinforcement that was added for flexural and for shear and crack control. So if I click on this information, it'll tell you that that's the total reinforcement that was added. The flexural reinforcement that was added was this 1661. The shear reinforcement added for the flexural the truss effect is 663 millimeters squared, and for service, or in other words crack control, it's added 80 millimeters or 79. And so that'll show you right along the length of the run. Down here you can see the capacity that's been achieved as a result of that reinforcement, and it shows you a number of things. Your minimum reinforcement required, so RAPT will always require you to have 1.2 times the cracking moment wherever the bending moment occurs on that face. Your ultimate design, which is your ultimate design bending moment, that's the same as the bending moment that we had in these bending moment diagrams over here. We have our initial capacity, which is the capacity we had before reinforcement was added, and then we have final capacity, which is the capacity after RAPT has added reinforcement. The graph at the bottom here shows you your neutral axis, and that gives you an idea of ductility. RAPT will always add reinforcement if you are not ductile enough. So if your neutral axis is above the code required amount, then RAPT will add reinforcement to ensure that you can redistribute moments if you want to. We have a serviceability information. So this is based on the SLS load combination, and this is telling you the compression in the this is the yellow line that we're looking here. This is the compression in the concrete under service load combination, and this is obviously occurring on the top. So anything with a solid line is on top. Everything with a dotted line is occurring at the top. So here I beg your pardon, I've done that the wrong way. So everything in the solid line is occurring at the top. So that's in sagging, we've got compression at the top of the slab, and then in hogging we've got compression in the bottom of the slab or the beam. If we click on the information button, it will give you the stress diagram, and you can see that there is a compression at the top, which is positive, and a tension at the bottom, which is negative. And that's your gross tension stresses based on an uncracked section. On a cracked section, RAPT then shows you what the stresses are for the concrete, and then tells you what the stress is in the steel, which is 306 MPa. If I go to the text output for the same thing, RAPT will tell you what the same information. So in other words, your gross uncracked stresses, top and bottom, your cracked section results, and it will add reinforcement in order to minimize or to keep these tension stress changes to required limits to the code. So normally RAPT will tell you what your maximum bar space is and your maximum spacing. But if it finds that it can't give you a spacing and a bar size that would limit your crack width to code requirements, and you can set the crack width that you want. Typically, if you don't change anything, RAPT will design reinforced sections to 0.3 millimeters and pre-stressed or post-tension to 0.2 millimeters. So if it can't find a solution to maximum bar size and spacing to the code, it will throw an error, and you can see an error here saying the maximum bar spacing is less than the code minimum spacing, and it will then add reinforcement to get you to a point where those code minimums are met. If, for example, RAPT is telling you that there is no reinforcement added, but you need to have 10 mil bars at 108 mil or 100 mil spacing, RAPT won't add that to the reinforcement. That's a guide for you to follow. If you want RAPT to add that information or those bar spaces, you can limit your stresses in your top and bottom your stresses in the reinforcement by putting in here a maximum stress change, and those maximum stress changes are defined in codes for certain bar sizes, and then RAPT will add the reinforcement in if you specify that. So back to our output, we now have a stress at the top and a stress at the bottom. A 0 here is just a rounding. It doesn't mean that there's no stress. You now can look at, again, there's a shear design. So in so this at the moment is not showing much for reinforcement required because we haven't set up the default legs at the moment. There's the reinforcement that is provided by the shear ties is actually too much, so it's not giving you any more information, any guidance on shear ties. So let's go back to our input and our default reinforcement. We can change our shear ties. We don't need as much as we've got there, so we'll make them lower grade. Let's keep them as 10s, and we'll keep that number as we've shown there. We go back to output, and you can see that RAPT is now showing the minimum number of legs that are required because there is a transverse shear space requirement. If I click on that, it'll tell you there's 3 legs required. So our 2 R10 is probably not enough legs. You need a minimum of 3. So we've got 4 and 6. Those are the 2 ones that would work. And if you look at the minimum number of legs, 3 legs using R10s, the spacing required would be spaced at 200. But if you've got 4 legs, we need to space it at 265, and at 6 legs, we need to space them at roughly 340. So for various different shear tie arrangements, number of bars and bar size and number of legs, it'll give you shear tie spacing, and you can choose the most appropriate one. Shear tie is not required in here because the concrete strength is enough where the shear is low at the supports. Down at the bottom, it shows you the concrete capacity. So the blue line there is the capacity of the concrete without any shear ties. The minimum capacity is the capacity of the, this is the shear capacity with the minimum amount of steel reinforcement. The minimum amount of steel reinforcement being the spacings given up here for various shear tie arrangements. And our green line, applied V, is the applied shear force, factored design shear force. Okay, we have the same information that's provided in text form. I go to shear beam design and I go to text, and we see the same thing being outlined here, which is our shear capacity with shear ties, our maximum web crushing capacity, our minimum shear design strength. Sorry, I beg your pardon. 5 VU min is the shear capacity with the minimum amount of steel added. 5 VU is the capacity of the concrete without shear reinforcement. That's the assumed angle that's been designed with for shear, and those are the spacing of the sets that we had before. Sometimes RAPT will add reinforcement if it is required for the shear offset rule. Sorry, in shear comments, this is just shear ties, so it's telling you that you need the minimum steel arrangements. Here you need no shear steel. For Eurocode, you will always need shear steel, even if you don't need the minimum amount required. You still need to put a nominal amount in. So we can go back. Now that we've done that, gone through our shear design, our flexural design. We've looked at crack control. We can now look at our deflections, and these are the deflections based on our design and RAPT's additional reinforcement that it's added as shown in those tables we looked at before. Based on the information that RAPT has given, and I should just outline here, the deflections here are shown are deflections including column shortening for that particular, for the column below. the deflection given down here is deflection from this point to a straight line at the top of the column here to the top of the column over there. And the span to deflection ratio is based again on the deflection relative to the tops of the columns. So that deflection is calculated based on the minimum ratio that the minimum amounts of reinforcement that RAPT has calculated as being required to meet code requirements. Then RAPT has also laid out additional reinforcement as one solution to meet those minimum amounts of reinforcement. So here is the layout that RAPT has provided. The brackets show the reinforcement that we added as user-defined reinforcement, 5 and 16s. And the other reinforcement that is not in brackets is the reinforcement that RAPT added to try and meet in as an efficient manner as possible the minimum reinforcement quantities at each design location. But this is just one solution of many. So this solution is a guide. It is not reflected in the deflections that we showed before. Those deflections are based on the minimum reinforcement amounts at each design location. This reinforcement layout may well provide slightly more reinforcement that's required at those locations. And there are obviously many combinations of reinforcements that would meet the those minimum amounts at each design location. So if you want to reflect this as a design, you need to go back to input, go to design reinforcement, user-defined reinforcement, and you click this button here which says insert design reinforcement pattern, and that will insert the reinforcement pattern that RAPT suggested on the run that you just did, and you insert that reinforcement as user-defined reinforcement. You can see it's now added all the reinforcement at the top and bottom as user-defined. We go back to output and you will see that RAPT has not added any more reinforcement because our reinforcement is all user-defined, and it will tell you what the deflections are based on this specific reinforcement layout, and you can see they are slightly different to what we had before. Previously we had about 25 millimeters. Now you can print that report out if you'd like, and that is the conclusion of a very quick RAPT run. Thank you.